in the early 2000s, medical researchers had this idea that, well, it seemed like just pure, undeniable logic.
Oh, yeah, the stent study.
Right, the stent study. Basically, if you have a patient who is at a super high risk of having a stroke because of narrowed blood vessels, the idea was, why not place a tiny expandable mesh tube-like, a stent, into those vessels to just prop them open?
Which makes perfect sense intuitively, right? Like you have a blocked pipe, you just open it up.
Exactly. So they set up this study, and they tested the procedure on 451 at-risk patients. But when the data actually came back, the results were, well, they were absolutely terrifying.
Yeah, it was the exact opposite of what the medical community anticipated.
Totally backwards.
Right, so the group of patients who actually received the stents, the treatment group, they had a 20% stroke rate. But the control group, the patients who received absolutely no stents at all, their stroke rate was only 12%.
So the treatment wasn't just, like, failing to help. It was actively causing harm.
Actively harming them, yeah.
An 8% difference in the completely wrong direction. Welcome to today's deep dive, everyone. We are exploring the foundational concepts of statistics today, really drawing on those core principles that govern how researchers collect, organize, and, actually test information.
It's so crucial right now.
It really is. The mission of this deep dive is to shortcut the path for you to be truly well-informed about the absolute bedrock of all modern science and news, which is data.
Because, data is literally everywhere you look today.
Exactly. We're going to demystify how this process works so you can spot bad science in your everyday life and understand what makes good science actually trustworthy.
Yeah, and that spent study is just a perfect example of why we can't rely on assumptions. No matter how logical they seem on the surface, understanding how to read data is a completely different skill than just collecting it.
Okay, let's unpack this. Because before we can analyze how data upends these massive, life-altering medical assumptions, we really need to understand how researchers organize the raw information they collect in the first place.
Right, because raw data is just a chaotic blizzard of numbers and notes.
Total chaos. So if we look at a data set from, say, a peer-to-peer lending company, the textbook uses this data set tracking 50 different loans. And here we see the foundational structure of basically all analysis, which is the data matrix.
The data matrix, yeah.
I always like to visualize a data matrix as this giant digital filing cabinet. So in this cabinet, every single drawer is a case or an observation, like one specific person's loan.
Okay, I like that analogy.
And then inside that drawer, every folder is a variable. So, the loan amount, the interest rate, or maybe whether the person rents or owns their home.
That filing cabinet visualization holds up perfectly, actually, because it highlights that not all folders contain the exact same type of information.
Right, they're measuring different things.
Exactly. And the type of variable you're dealing with strictly dictates what kind of mathematics you're allowed to apply to it. If you categorize a variable incorrectly, your entire analysis it falls apart.
Well, let's break that down, because I think people assume it's just numbers versus words. But it's more complex, right? First, you have numerical variables, which are, numbers you can actually do math with.
Right, but there's a really crucial split even within numerical variables.
Right, you have continuous variables like an interest rate or an unemployment rate. Those can be measured down to basically any microscopic fraction of a decimal point.
Yeah, exactly.
But then you have discrete variable.
And discrete variables are strict counts. So think like the population of a town or the number of bedrooms in a house.
You can't have half a bedroom.
No, exactly. You can have an unemployment rate of, say, 4.392%, but you absolutely cannot have 2.5 people living in an apartment.
Right.
It has to be a whole number. It jumps discretely from 1 to 2 to 3. And if a researcher accidentally treats a discrete variable like it's a continuous one, their mathematical model might try to predict that a family will have 2.4 children.
Which literally breaks the physical reality of what they were trying to study.
Yeah, precisely.
Okay, so then completely separate from the numerical side, we have categorical variables. And these are basically descriptive buckets, but again, there's a vital split here too.
Yeah, nominal and ordinal.
Right, first are nominal variables, which are just entirely unordered. So going back to the loan data, a nominal variable would be the state a borrower lives in.
Right, like New York or California?
Exactly. New York isn't inherently higher or lower or, better than Maryland or California. They're just fundamentally different labels.
But then on the other side of categorical data, you have ordinal variables. And these are categories that actually possess a natural inherent ranking.
Okay, like what?
Think about education levels. So you have high school diploma, then some college, then bachelor's degree.
Oh, I see.
Right. They aren't numbers you can just average together, but there is a very clear progression there.
There's an order to them. Ordinal.
Exactly. And if you ignore that progression and treat an ordinal variable like a nominal one, you are basically throwing away massive amounts of context. You're treating a bachelor's degree and a high school diploma as if they're just random, unrelated labels like New York and Maryland.
It's amazing how just naming the structure of the data makes it feel so much less intimidating. We are literally just categorizing the folders in the filing cabinet so we don't accidentally use the wrong map.
That's exactly what it is.
But let me push back for a second here and bring this all the way back to the stent study.
Okay, sure.
So we were looking at a numerical difference there. The stent group had a 20% stroke rate, and the control group had a 12% rate. That's an 8% difference.
Right.
But couldn't that just be, I don't know, a natural fluctuation? Like, if you flip a coin 100 times and you get 60 heads instead of the expected 50, how do we know the stents were actually to blame? And it wasn't just a string of really bad luck for the people who happened to get them.
What's fascinating here is that you've just articulated the core reason the field of statistics even exists.
Oh, really?
Yeah. I mean, you expect 50 heads in a coin flip, but getting 55 or 48 is completely normal.
Yeah, that just happens.
Right. That is natural variation, and it is literally built into the fabric of the universe. To figure out if that 8% difference in strokes is just bad luck, researchers have to measure the observed difference against the size of the sample.
Okay. Because flipping 60 heads out of 100 is way more likely than, say, flipping 6,000 heads out of 10,000.
Precisely. The larger the difference and the larger the group of people you actually test, the less mathematically believable it becomes that the difference is merely random chance.
That makes sense.
Statistics basically provides the mathematical tools to definitively reject the notion that an observation was just a fluke. In the stent study, analyzing 451 patients revealed that an 8% gap was so massive that random chance was essentially impossible.
So it crossed that line.
Yes, it crossed the threshold into being what we call a statistically significant difference.
Okay, so once we trust that the data is real and we know exactly how it's structured into these different variables, what happens when we look at two variables together? Because, I mean, that's what we usually care about, right? How one thing interacts with another.
We want to spot patterns, and the absolute most effective visual tool for that is a scatter plot. Imagine a graph that is just dotted with thousands of individual points.
Let's use real census data from United States counties to picture this. So if we take thousands of counties and we plot the percentage of multi-unit structures like apartment buildings on one axis and homeownership rates on the other axis, the dots form a very distinct downward slope.
A negative association.
Right. Counties with more apartments consistently show lower homeownership rates.
And it reflects a logical reality, right? If a county is entirely dominated by high-rise apartments, the vast majority of the population there is renting, which naturally drives the overall homeownership rate down. As one variable goes up, the other goes down.
Conversely, if you look at median household income plotted against population growth, you see a positive association.
Exactly.
As household income moves higher up the graph, the population growth also trends upward. Higher incomes correspond to higher growth.
Whenever researchers look at these relationships, they almost always bring a hypothesis to the table. They suspect that one variable is the actual driving force behind the change in the other.
Okay, so they assume a relationship.
Right. We call the driving force the explanatory variable, and the outcome is the response variable. So we hypothesize that the median household income, the explanatory variable, is influencing or explaining the population growth, which is the response variable.
But here's where it gets really interesting, because the bedrock rule of all data analysis emerges right here. Association does not equal causation.
The golden rule.
It is. Just because two variables move together in perfect harmony on a scatter plot absolutely does not mean one is causing the other to happen. The textbook has this classic example of observational data that shows a very strong, undeniable link between sunscreen use and skin cancer.
Oh, this is a great example.
It shows that the more sunscreen someone applies, the more likely they are to develop skin cancer.
Which sounds terrifying. If you simply looked at that raw association on a graph, you might panic and throw away all your sunscreen, just assuming it was highly toxic.
It's like noticing that people who carry umbrellas often have wet shoes, and boldly concluding that umbrellas cause wet shoes, completely ignoring the rain.
That is a perfect analogy. In statistics, that rain is what we call a confounding variable.
A confounding variable.
Right, it's the hidden third factor that influences both of the variables you are actually measuring. So in the sunscreen example, the confounding variable is sun exposure.
Of course.
Right, a person who spends all day at the beach in the glaring sun is far more likely to apply sunscreen. But that exact same person is also far more likely to develop skin cancer from all the UV radiation.
So the sunscreen isn't causing the cancer at all.
No, the sun exposure is causing both the sunscreen use and the cancer.
Wow. So if we don't aggressively hunt for confounding variables, we end up blaming the umbrella for the puddles.
Exactly. And if we connect this to the bigger picture, this is exactly why observational studies are so incredibly treacherous if you try to use them to make definitive causal claims.
Because they just watch.
Yes. An observational study is when researchers simply collect data as it naturally exists in the world, like reviewing a decade of medical records or, sending out a survey about dietary habits. They just watch. They don't interfere. They don't assign treatments.
They're essentially just taking notes from the sideline.
Yes, and while observational studies are fantastic for finding associations and helping us form new hypotheses, you can literally never be 100% sure you have accounted for every possible confounding variable hiding in the background.
So if observational data is full of hidden traps like sun exposure, how do we get data we can actually trust to prove a cause? I mean, if we can't just observe naturally occurring data, we have to go out and capture our own data. But you can't realistically test every single person on Earth.
You definitely can't. Which brings us to the absolute foundation of setting up a reliable study, which is sampling.
Got it.
You have your population, which is every single entity you want to know about. Let's say you want to study the mercury levels in all the swordfish in the Atlantic Ocean.
Catching every single swordfish is impossible.
Right, it's physically impossible. So you have to capture a sample, a small fraction of the population that hopefully accurately represents the entirety of the ocean.
The problem is the human brain is notoriously terrible at intuitively understanding what a representative sample actually looks like.
Oh, you're awful at it.
We default to anecdotal evidence. Like
Yeah.
back in February 2010, when a massive historic snowstorm hit the East Coast, and media pundits used that single weather event to claim global warming was a hoax.
Yep.
Or, you might know two people who took 7 years to graduate from a specific university, and you just permanently hardwire your brain to assume that university is impossibly difficult to graduate from.
We cling to anecdotes because the human mind is naturally drawn to a compelling narrative. We remember the extreme cases. But those two students who took 7 years to graduate, they only represent highly unusual, extraordinary circumstances.
They were outliers.
Completely. They tell you absolutely nothing about the true average experience of the entire student body.
To avoid the trap of anecdotes, researchers have to systematically select their samples. But even trained professionals can mess this up badly.
Very easily.
There's convenience sampling, which is exactly what it sounds like. If you want to understand the political leanings of the entirety of New York City, but you only survey people walking past you on a single street corner in the Bronx just because it's close to your office, your data is ruined.
You've completely ignored Staten Island, Manhattan, Brooklyn, and Queens.
Exactly.
You also have to aggressively guard against non-response bias.
What's that?
Let's say you mail out a survey to a perfectly balanced, random group of 1,000 citizens, but only the 200 angriest, most polarized people actually bother to fill it out and mail it back. Oh, right.
Your sample is no longer representative. You've only captured the extremes of the population, leaving out the entire moderate middle.
So if convenience sampling is useless and non-response bias is a constant threat, how do researchers actually capture a fair sample without, going bankrupt?
They rely on 4 highly rigorous sampling methods. The most straightforward is simple random sampling. It operates basically just like a giant raffle drum. Every single case in the entire population has an exactly equal chance of being drawn. It is elegant and theoretically completely fair.
But sometimes a giant raffle drum isn't enough, right? Which introduces the second method, stratified sampling.
Yes.
This is a brilliant divide-and-conquer strategy. You divide your population into distinct groups called strata, where the cases inside each group are very similar to each other.
For example, if you wanted to analyze the salaries of Major League Baseball players, you wouldn't just use a simple random raffle of all the players. You would first group the players by their team. Those are your strata. Then you pull a random sample of players from within each individual team.
Exactly.
But wait, let me push back again. Why go through the complex logistical hassle of stratified sampling with the baseball teams? Isn't a giant, simple, random raffle bucket with all the players' names inherently unbiased? Why complicate it?
It is unbiased, yes, but a simple random sample relies entirely on luck.
Okay.
If you just draw names from a giant bucket, sheer statistical variance might cause you to accidentally pull a disproportionate number of players from the richest franchises, like the Yankees or the Dodgers.
Oh, I see.
Right? You might completely miss a low-budget team just by chance. By using strata, you mathematically guarantee that every distinct subgroup from the wealthiest franchise to the poorest is perfectly and equally represented. It provides a level of stability and precision that pure luck simply cannot guarantee.
That makes a ton of sense. You are basically building structural guardrails against the extremes.
Exactly.
But what if your population isn't neatly organized into baseball teams? What if it's massively spread out geographically?
That is where the final two methods come in: cluster sampling and multi-stage sampling. Let's say you need to test the population of rural Indonesia for malaria.
Okay.
If you used a simple random sample across the whole country, you might end up having to charter a helicopter to fly to 30 different highly remote villages just to test two randomly selected people in each village.
That'd be an economic nightmare. You'd spend millions on helicopter fuel just to test 60 people.
Exactly. So instead, use cluster sampling. You break the population into clusters, in this case, the villages themselves.
Okay.
You randomly select, say, 10 entire villages, and you fly out and test every single person living in those 10 locations.
Wow, that's way more efficient.
And multi-stage sampling takes it one step further. You randomly pick those 10 villages, and then you take a random sample of individuals strictly within those 10 villages.
So you are containing the logistics. You save massive amounts of time and money. But because you randomized which villages you visited, you preserve the mathematical integrity of the study.
Precisely. You sacrifice a microscopic amount of statistical purity for real-world viability, because if a study is too expensive to run, it never happens at all.
Okay, so we've carefully avoided convenience sampling. We have our perfectly selected, mathematically sound sample. How do we finally cross that massive chasm from association to causation? How do we definitively prove the umbrella didn't cause the wet shoes?
You have to run a randomized experiment. You have to actively take control of the variables. And there are 4 non-negotiable principles of experimental design.
4 principles.
The first is controlling. Researchers must ensure that the only difference between the two groups is the treatment itself. If you are testing a new pill, you have to ensure every single patient takes it with the exact same 12-ounce glass of water at the exact same time of day.
Because if the treatment group drinks water and the control group doesn't, you won't know if the pill made them feel better or if they were just hydrated.
Exactly. The second principle is randomization. You randomly assign the patients to either the treatment group or the control group. This is how you handle those confounding variables you can't see.
Like the sun exposure.
Right. By randomizing, you ensure that unknown factors like rare genetics or hidden dietary habits are evenly distributed across both groups. It basically evens the playing field.
And the third principle is replication. A study of 4 people isn't a study, it's an anecdote. You need a sufficiently massive sample size to accurately estimate the effect.
Right.
And the methods must be so transparent that another lab across the world could replicate your study from scratch and get the identical result.
Which brings us to the fourth and perhaps most vital principle: blocking.
Blocking.
Let's say you are testing a powerful experimental heart drug. If you rely purely on random assignment, there is a tiny statistical chance that all the 80-year-old patients end up in the treatment group and all the 30-year-old patients end up in the control group.
Oh, wow. The age difference would completely ruin the data.
Exactly. So you block for it. Before you randomize, you separate the patients into a high-risk block and a low-risk block. Then, you randomly assign half of the high-risk block to the treatment and half to the control, and you repeat the process for the low-risk block.
It's like stratified sampling, but applied directly to the experiment itself.
Yeah.
You're preemptively neutralizing a variable, could destroy your results.
Precisely.
But even with controlling, randomization, replication, and blocking, human biology and psychology are incredibly messy. We introduce bias just by being aware of what is happening, right?
Oh, absolutely.
If a patient knows they are taking a highly touted experimental drug, they might miraculously start feeling better just from the sheer optimism.
And to counteract that human psychology, researchers use blinding. The patients cannot know which group they are in. And since people in a control group would obviously notice if they weren't taking a pill every morning, Researchers use placebos,
Sugar pills.
right? Inert, fake treatments.
But the doctors administering the pills are human too. They have biases.
Which is why the absolute gold standard is the double-blind setup. If a doctor knows they are handing a dying patient the real life-saving medication, they might subconsciously give that patient more reassuring smiles, more attentive care, or more frequent check-ins.
And that extra attention becomes a confounding variable.
Exactly. In a double-blind study, neither the patient nor the doctor interacting with them has any idea who holds the real drug and who holds the sugar pill. The data is entirely insulated from human hope and bias.
So what does this all mean? The mechanics of a double-blind study are brilliant, but they lead to a scenario that really stops you in your tracks when you think about it.
You mean the surgical controls?
Yeah. To maintain a purely blind study for a physical surgical procedure, researchers sometimes rely on sham surgeries.
Yeah.
They will literally put a patient under heavy anesthesia, make a physical incision with a scalpel, manipulate the tissue to make it feel real, and sew them back up without actually performing the medical procedure. All just so the patient believes they had the surgery and can serve as a pristine control group.
It is intense.
Is it really okay to physically slice someone open for a fake sham surgery just to satisfy the mathematical requirements of a control group? That feels like crossing a massive fundamental line of medical care.
This raises an important question, and it is undoubtedly one of the most intense, fiercely debated ethical dilemmas in modern scientific research.
I can imagine.
You are intentionally subjecting a human being to the risks of anesthesia, the risk of a hospital infection, and the physical pain of recovery, knowing they are receiving absolutely zero physiological benefit.
Right.
On an individual level, it directly conflicts with the core medical oath to do no harm.
It feels like an incredible violation of trust.
It does. But researchers are forced to weigh that individual harm against the utilitarian ethics of the entire future population.
A greater good argument.
Exactly. The harsh reality is this. If we don't utilize placebos or sham surgeries to extract pristine causal data, we risk approving a costly, entirely useless, or potentially lethal treatment.
Wow.
And we would then promote that harmful treatment to millions of desperate people over the next few decades. The sham surgery, as difficult as it is to stomach, is the ultimate shield protecting the future population from bad science. It is a terrible situation where perfectly protecting the brave volunteers and perfectly protecting millions of future patients are in direct, unresolvable conflict.
It profoundly puts the immense responsibility of gathering data into perspective. These aren't just abstract numbers organized in a matrix. These are actual people's lives on the line.
They absolutely are.
Well, let's recap the journey we've taken today. We started by organizing the raw chaos of information into data matrices, separating continuous numbers from ordinal categories to make sure our math doesn't break reality. We learned how to spot patterns using scatter plots, while aggressively avoiding the deadly trap of assuming that an association guarantees causation, always looking out for the rain behind the umbrella.
Essential.
We explored how to bypass the allure of anecdotal evidence through rigorous, randomized sampling methods, from simple raffles to complex cluster logistics. And finally, we uncovered how to definitively prove causation through the strict, occasionally ethically agonizing architecture of double-blind, randomized experiments.
It is a phenomenal toolkit for navigating an incredibly noisy world.
And it has immediate practical value for you, the listener. The next time you're scrolling through the news and you see a flashy headline claiming drinking coffee causes heart disease or this new superfood cures everything, you no longer have to just take their word for it.
You really done
You have the toolkit to interrogate the claim. Was this merely an observational study? Were there massive, confounding variables the researchers entirely missed?
Did they control for sun exposure?
Exactly.
Yeah.
Was the sample actually representative of the population, or did they just convenient sample 20 college students on a Tuesday afternoon?
You gain the ability to look right past the sensationalism and analyze the actual architecture of the claim.
Exactly. I want to leave you with one final provocative thought to mull over, based on something we touched on with blinding, which is the placebo effect.
Oh, this is fascinating.
Sometimes, taking a completely fake sugar pill results in a slight but entirely real and scientifically measurable improvement in a patient's physical health.
Which is mind-blowing.
It is. If human biology can actually alter itself, if physical symptoms can genuinely diminish simply because a person believes they are receiving real medicine, what is the data actually measuring in those moments?
That's the question.
Is the clinical data capturing the chemical efficacy of a drug? Or is it capturing the sheer physiological power of human belief.
It's a reminder that data doesn't just measure the external mechanics of the world. It acts as a mirror reflecting our own profound internal complexities.
It really is. So the next time you're faced with a murky situation and you're wishing for a clean, simple answer to show you exactly where the truth lies, remember that the absence of an easy answer isn't the end of the inquiry.
Not at all.
It's just the invitation to look deeper. You just have to know how to structure the data. Thanks for joining us on this deep dive. We'll catch you next time.